Okay, in this video, we're going to talk about weak acids. This is really part 2 of a pair of lectures on weak acids and calculations using ice charts on weak acids. Today, we're going to focus on a calculation where we try to come up with the pH of a weak acid using the Ka. In the previous video, go back and watch it if you didn't, we calculated Ka given the pH. Now we're doing the reverse. We're calculating pH using Ka. And here's the method we're going to use. Always you want to write the chemical reaction out, okay? And then write your Ka out, okay? So write reaction, write Ka, set up ice chart, and then solve the ice chart and go from there. So these are things you can read through and memorize, but it's really best to learn these things by doing an example. So let's look at an example here. Let's calculate the pH of a 0.30 molar solution of acetic acid written here. And you're given the Ka value. And this is, in practice, what is usually going to happen for you. You'll be dealing with some acid in the laboratory whose Ka is well known, but you're preparing a certain type of that acid, certain concentration, and you want to know its pH. So the first thing to do is to write the reaction. That's what we've done here. HC2H3O2, that's the citric or acetic acid, plus water makes H3O plus this conjugate base of the acetic acid, acetate ion. We can write Ka, it's always products over reactants. Remember, we don't include water since it's a liquid. We only include aqueous and gaseous things and equilibrium constant expressions. For these acids, these Kas, it's always going to look like this, H plus or H3O plus, the conjugate base over the original acid. Now, step 3 is to set up the ice chart. So let's think about, for this reaction, we don't need to include water really, so our ice chart is going to be divided sort of down the middle here. We're going to have a column for H3O+, we're going to have a column for acetate ion, and we're going to have a column for acetic acid. It's my initial, change, equilibrium. Now, what do I know about this problem? Calculate the pH of a 0.3 molar solution of acetic acid. Remember, this is my initial. This is before the acid started dissociating. So this is the initial amount of the acid. And implied here is that it hasn't dissociated yet. It hasn't been able to achieve an equilibrium or even start, really. So these are going to be 0. Now, in the previous type of problem where we were given a pH, we were able to figure out the H3O plus at equilibrium because we had the pH. 10 to the negative pH is the concentration of H3O plus at equilibrium. But here we're asked for the pH. So this is all the information we have. How do we go about solving this? Well, we do have the Ka expression. That's going to come in handy. But we can't enter anything else here in the ice chart as a given number, but we can use algebra. So remember, if there is a side of a reaction that is 0 to start with, those have to go up. So the products must be increasing, which means if the products are going up, the reactants are going down. So I'm just going to hold some placeholders, pluses and negatives here to symbolize that. Now, I can also look through here and see that everything is balanced and everything is a 1-to-1 ratio. Do make sure the reaction is balanced as you wrote it. This looks good, and everything's 1-to-1. So I'm just going to use x here to signify that these went up by some amount x. Right? You can write 1x, you can make it y, you can use whatever you want here, right? But it's an unknown amount. But if these went up by an amount x, then this went down by x. And so I do have a way to express my equilibrium concentrations with regard to a single variable x. And now I have everything I need with respect to one variable because I have this acid dissociation constant, right? What is Ka? Ka is equal to these equilibrium values. So this Ka value is going to equal x for H3O plus, x for the acetate ion, x times x is x squared, over the reactants, 0.30 minus x. And this is an equation here where we can rearrange and use the quadratic formula. Okay, so I took you through all of that, but let me write it a little bit more clearly so you can read all of this. So it'll look something like this, right? Here's my acid, here's the H3O plus, here's the acetate. My Ka value is still this 1.8 times 10 to the negative 4 equals x squared over 0.30 minus x. Rearrange and use the quadratic formula. So I can do that. I can take this 1.8 times 10 to the negative 5 equals x squared over 0.3 minus x. I can multiply both sides by this 0.3 minus x. Okay, I can distribute this to both, write that out. I can then move everything here to the other side so that I can get it in a quadratic form that looks like 0 equals x squared, right, minus 1.8 times 10 to the negative 5x, right, plus whatever 1.8 times 10 to the negative 5 times 0.3 is. That'll go here. And now you have your A, B, and C, and you can use the quadratic formula. Or I'm going to show you a trick here. And the trick is really just an approximation. So we can use the quadratic formula. At the end, if you do this, you'll get an H3O plus concentration that corresponds to a pH of around 2.6. Okay, but let me show you the trick that's going to make it much simpler than having to get the quadratic formula involved. And the trick is the following. The trick is we've seen for strong acids a complete dissociation of the acid into making a bunch of H3O plus. But for weak acids, this is quite small. So this X is quite a small number because weak acids don't dissociate much and don't create much H3O plus. And so what happens is you have a very tiny number here for X, such that 0.3 minus X, 0.3 minus X, is about equal to just 0.3. Because if X is really, really small, then 0.3 minus something really small is still basically 0.3. So an approximation you can use here is if X is really small, just drop it from the denominator. And now this equation is much easier to solve. You just multiply both sides by 0.3 and take the square root, and you have your X. You don't have to get the quadratic formula involved at all, and students really like that. Okay, so let's see how that's borne out. If we drop this X here, we're assuming the X is very, very small, which we'll test, but is probably a good assumption for a weak acid. So 0.3 minus X, minus a small number, is just 0.3, and the problem becomes much easier. Okay, so we'll have 1.8 times 10 to the negative 5 equals x squared over 0.3. We'll multiply 0.3 by both sides. We'll take the square root, and our x value will be 2.3 times 10 to the negative 3. And remember, this x value we're after is our equilibrium amount of H3O plus. What we're after in this problem is the pH, so it's just negative log of this x. That's our pH. That's what we're after here. And negative log of this number is 2.64, which is pretty similar to what we get from the quadratic formula. So it's usually a pretty good approximation in these weak acid dissociation problems to drop the x here in the denominator of this equilibrium constant or acid dissociation constant expression that you've set up. Okay, now the rule here, right? This was using an assumption, okay? Is it valid? When is the assumption not valid? Is this valid? Okay, so we went through all this. We found our overall pH, but was this safe to do? And this is the question you need to ask yourself once you get and calculate X quite easily, right? If X is less than 5% of HA, the initial acid concentration, HA initial, then it's safe. Right? If not, then you go back and use the quadratic. And so most of the time it will end up being safe. So it's good to assume this and check it rather than always do the quadratic formula, because that often takes a lot longer. Now, if you want to be much more precise with your final answer, then the quadratic formula makes sense. But most of the problems that we'll do in these lectures, in the classes I teach in general chemistry, it's going to be worth it to assume this, check the assumption. Most of the time it will be yes, and you'll be on your way and you've solved the problem. If it's not, then you have to go back and use the quadratic. So let's just verify here that, yes, it's safe, right? Let's look at this value that we've got for X. Is it less than 5%? So we'll do 5 over 100, 5% of the initial acid concentration. The initial acid concentration was this 0.3, right? And so what we're saying here is this value of X that we're neglecting much smaller than this, such that it's not changing it. Okay, so is this X value smaller than 5% of, in this case, 0.3? Well, 5% of 0.3 is 0.15. Sorry, 0.015. And yes, 0.0023, 2.3 times 10 to the negative 3, is indeed less than 5% of my initial acid concentration. So yes, this was safe to do. I can trust this pH value is close enough for our work here. Okay, so this is going to be the route we take for these calculate pH of a weak acid problems, something you're going to have to do lots of times in your general chemistry courses or in any chemistry lab when you're making weak acid solutions. Write the reaction, write your equilibrium constant expression, make your ice chart. Use the assumption if you can, right? And really it should say, make the assumption, go back and see if it was safe to make that assumption, because it makes solving for X that much easier. Okay, one last thing. Let's try a practice problem first before we get to the one last thing I want to talk about in this lecture. So let's put this into practice. We have the roadmap of what we have to do. We just went through a problem trying it. So now this is a great time for you to practice. Pause the video here and try this problem yourself to calculate the pH before watching me solve it. Okay, so step 1 is write the reaction, HCN. You can do plus water goes to H3O plus, but I take shortcuts here and I just say, well, it's aqueous, we know it's in water, it's making H plus, that's sort of synonymous here with H3O plus. Okay, plus my conjugate base, the acid without the H plus, that's CN minus. Okay, so here's my reaction. I can write my expression for Ka. I know my Ka value here is going to be 4.9 times 10 to the negative 10. Okay, and that's going to be my H plus at equilibrium, Cn minus at equilibrium over HCN. And, just looking at this and comparing it to the previous problem, it's probably going to look something like x squared over this minus x, right? But until you do a lot of these, and we'll see as we move forward in this class that these are going to get more complicated once we start getting into acid-base titrations, right? It's not always safe to do these things, so we want to go through the effort now to actually write the ice chart out, because we're going to have to keep making these when we talk about more complex aqueous equilibrium problems. So let's see, initially 0.20 molar of HCN, so that goes here. These are 0. It was only HCN to start. These, since they're 0, are going up by some amount. It's a balanced reaction. Everything's 1 to 1, so I'll call these plus 1x, or just plus x, and this is minus x. So 0 initial plus change plus x is x. 0 plus x equals x. Same for Cn minus, 0 plus x equals x. For HCN, it's 0.2 minus x, and so the equilibrium is 0.020 minus x. Okay, and now I have my equilibrium values. So H plus, that was x. Cn minus, that was x. HCN, that's 0.2 minus x. Okay, so this numerator is really x squared. Now, let's assume x is small. And so we can neglect it. This then becomes 4.9 times 10 to the negative 10 equals x squared over 0.2. Okay, so now this is pretty simple to solve. We multiply both sides by 0.2, so we have 4.9, we have 0.2 times 4.9 times 10 to the negative 10 equals x squared. Take the square root of both sides. That's going to equal our x value. And here we get an x value of 9.9 times 10 to the negative 6 molar. Okay, where really that represents here my H plus concentration. I can test, is this 9.9 times 10 to the negative 6 less than 5% or 5 over 100 of my initial concentration 0.2, and 9.9 times 10 to the negative 6 is indeed less than 0.01. So yes, safe. And so to get the pH, I just do negative log of this H plus concentration. And so here that will be 5.0. Okay. Now, this is a acid, but it's a very weak acid. So the pH, while acidic, should be just not very acidic. So 5 is less than 7. It's definitely acidic, but it's not super acidic, right? Back here, we had something that was a much stronger weak acid. And so the pH was a much lower number, 2.64. So conceptually, this all sort of seems to check out. Okay, so that's weak acid dissociations where you're calculating pH. The last thing I want to mention here is a polyprotic acid. So poly means many, protic for protons. So these are acids that have multiple protons to donate. When we were talking about our list of strong acids several lectures ago, we had things like HCl, right, and HNO3, all strong acids, but we also had H2SO4. That is technically a polyprotic acid because while it donates a single H plus to make HSO4 minus, it has another then proton it can donate, right? So this H2SO4 is essentially a one-way arrow to make H plus plus HSO4. But this HSO4 might then be able to also create a proton. And it is able to do that. Now, since the first proton is so one way, right, and the second process is an equilibrium, basically all of the pH is attributed to this first proton. Okay. It's always easier to remove this first proton than any proton after that. But for this strong acid here, it's really only this first dissociation that matters. And indeed, for any difference in Ka values, right, of 3 or greater in terms of the exponent, the pH generally depends only on the first dissociation. So you can look at some of these other polyprotic acids. Here you have phosphoric, one of the most common here. And the first acid dissociation constant is labeled Ka1. The second, for the second proton, Ka2. The third, Ka3. And let's look at how these values of the Ks decrease. For phosphoric, it's -3. The second is -8, quite a big leap. The third, -13. So these Ka2 and Ka3 for phosphoric are so small compared to this Ka that the amount of H plus they create, the amount they disassociate, the percent ionization is really, really small by comparison. So you're not getting a ton of protons, H plus, hydronium, from these processes compared to this one. Okay, so if the difference between this exponent here and this exponent here is 3 or greater, we generally don't worry too much about these first affecting the pH. Okay, citric acid here is -4, -5, -7. So these are close enough that you have to worry about each of these successive processes. So here there was 2 for this citric acid. You could write 3 for the first proton, the second, and the third of these H3, 3 protons that you can make. And you would have to do multiple ice charts and multiple ice tables. Okay, so those are polyprotic acids where they have more than one acidic proton, and it's always easier to remove the first. The acid is stronger with the first dissociation than any successive dissociation. And we only really worry about these successive dissociations in the event that the Ka values are closer than, say, a factor of 3. That's the approximation I like to use. All right, so that'll do it for this lecture where we talked about polyprotic acids here at the end, but really focused on using ice charts to figure out the pH of weak acids. In the next lecture, we'll transition and talk about weak bases before we end with lectures on different types of acids like oxyacids and carboxylic acids. So that'll do it for this lecture. See you next time.